Hello. This video includes information on thermal energy, temperature, and heat. It will also discuss heat capacity and calorimetry. When we talk about energy, we first need to have a working definition. So, energy can be defined as the capacity to supply heat or to do work. There are two categories of energy: potential energy, which is the energy an object has because of its relative position, composition, or condition, and kinetic energy, which is the energy an object possesses due to its motion. We also need to know about the law of conservation of energy, which is sometimes referred to as the first law of thermodynamics. It states that energy can be converted from one form to another, but all of the energy present before a change has to be equal to the energy after that change has been completed.
So the classic example of kinetic energy versus potential energy is looking at a roller coaster. So, you've got the car up at the top of the hill. It's got a high potential energy because of its relative position. As it starts to roll down the hill, it picks up speed and the potential energy goes down and the kinetic energy goes up. So when you get to the bottom of the hill, the kinetic energy is at its highest and the potential energy is at its lowest. And then as it moves back up the hill, the kinetic energy is converted back to potential energy, and the molecule is at its highest potential energy and lowest kinetic energy here. And that process just continues on down the roller coaster. So when we deal with thermochemistry, there are kind of three terms that are often mixed up and don't necessarily mean the same thing. So thermal energy is the kinetic energy associated with the random motion of atoms or molecules in a sample. Versus temperature, which is a quantitative value, which gives us an indication about how hot or how cold something is. So if we were to look here, okay, you've got a thermometer, which helps to measure how hot or cold something is, the temperature, because the liquid that's in that thermometer, as it gets hotter, okay, it expands. And as it gets colder, it contracts. So we can read the temperature on a thermometer. Or if we were to look at thermostats, okay, thermostats sometimes work like this, where you've got metals that contract and expand based on their temperature. And that's what kind of clicks on the heat or clicks on the air conditioning. So when we deal with heat, heat is the transfer of thermal energy between two substances or between two bodies. And the bodies would initially be at different temperatures. So heat is a transfer of thermal energy. When you say something's being heated up, energy is being transferred from one substance to another. And the energy will always be transferred from where it has a higher average kinetic energy to a lower average kinetic energy. So if we were to look at a picture here, okay, we've got a substance here that's hot. Okay, it's hot water. So it's got a high thermal energy. And we've got cold water here. It's got low thermal energy. And if we were to have the two water samples in contact with each other, that energy is going to start to be transferred from where it's higher in the hot water to where it's lower in the cold water. And the energy will continue to be transferred from high to low until the average kinetic energy of the particles, the temperature, is the same. And then we have what's called thermal equilibrium. It essentially just means that the thermal energy here is equal to the thermal energy here. At that point, the energy transfer stops. Now, if this were not an insulated container, then maybe some of the energy from the system, what we're looking at here, might be transferred to the surroundings. Okay, but we're looking at a closed system here. So heat is the transfer of thermal energy from high to low until thermal equilibrium is established. So when we look at matter and it either undergoes a chemical reaction or a physical change, energy is associated with that process. Either energy is released or energy is absorbed during that chemical or physical change. If energy is released, the process is called exothermic. Exo means exiting. So thermal energy is flowing from the system into the surroundings. Thermal energy is exiting the system in an exothermic process. When we talk about an endothermic process, we're looking at energy that's being absorbed by the system from the surroundings. Endo means into or entrance. So in this case, energy is flowing from the surroundings into the system. So if we were to look at an example of an exothermic reaction, okay, here we have our blowtorch, okay, which is giving off energy. So that's an exothermic process. And the energy that's being given off during that exothermic process is being used to melt the metal so that it can be cut. If we talk about cold packs, okay, you have them maybe in a first aid kit. Okay, cold packs are an example of an endothermic process. And what they actually are made of, if we were to look inside a cold pack, we have an inner compartment, okay, which contains some water. And we have the outer compartment, which has a chemical called ammonium nitrate. And if you twist or punch the whole cold pack, you break the inner bag, the water mixes with the ammonium nitrate. And when the ammonium nitrate dissolves in the water, it absorbs energy out of the surroundings. So it's called an endothermic process. Now, the energy that's being absorbed into the cold pack is coming from your hand. And that's why your hand gets cold, because energy is flowing from your hand into the cold pack. So we've got an example of an endothermic process here and an exothermic process here. So let's look at a couple of examples and see if we can decide whether the process is a endothermic process or an exothermic process. Our first example, a person's hand becomes cold upon touching ice. So you want to talk about it relative to the person's hand. Is the hand losing energy, or is the hand absorbing energy? The hand is losing energy, which is exothermic. Now, that's relative to the hand. Think about where that energy is flowing into. So now we're going to look at it from the other side. The ice gets warmer upon touching it. So relative to the ice, is that endothermic or exothermic? The ice is endothermic, right? Energy is flowing from the hand into the ice. So the hand is losing energy. Energy is exiting the hand. So that makes it exothermic. And that energy is flowing into the ice So the ice is gaining energy. So that's endothermic. So here's another example. Water boils in a kettle being heated on the stove. So we want it relative to the water. Okay, is the water exothermic or endothermic? It's being heated up by the stove. Water is flowing into the water to cause the water to boil. So that's endothermic. So if we wanted to talk about it relative to the stove is giving off energy. So energy is flowing from the stove into the water. Water vapor condensing on a cold pipe. Think about that for a second. Water condensing on a cold pipe. It's actually a little bit hard. I have a hard time kind of conceptualizing this. So think about, water condensing, it's going from a gas to a liquid. Think about what that water does when it goes from a liquid to a gas, and it's just the opposite. It's a little bit harder to conceptualize. So think about it this way. Ice cream melts. Okay, so we've got the solid ice cream, and it's turning to a liquid. Is the ice cream absorbing energy? That would make it endothermic. Or is the ice cream being giving off energy, and that would make it exothermic? So ice cream melting. It's absorbing energy from the surroundings. So the ice cream, relative to the ice cream, it's endothermic. Okay, so water freezing. So water's going from a liquid to a solid. Yeah, that's exothermic. And again, that's kind of hard to visualize. If you think about it the other way around, in order for water or ice to melt, you have to add energy in. Okay, that makes sense. So if ice or if water is freezing, which is the opposite, that would be exothermic. We're going to move on and start to put some numbers to our thermochemistry unit. And let's look first at the units that are going to be involved in energy. So when we talk about energy, okay, historically, the unit for energy was a calorie. Okay, now that's an English system unit, kind of like saying inches. And it's the amount of energy required to increase the temperature of 1 gram, 1 degree Celsius. Okay, the more modern unit that's used is a joule. Okay, and the symbol that we use for that is a capital J. So you really will not see anything math-wise that involves calories, but you're going to be dealing with the units of joules. And when we talk about joules, it's the amount of energy used when 1 Newton of force moves an object 1 meter. Now, I should have put this first. Relating these two units, 1 calorie equals 4.184 joules. Now, to kind of talk about this concept here just for a second, when we talk about work, okay, work is equal to force times distance, where our force is in newtons and the distance is in meters. But we can do some converting with those units. A joule, which is what we're dealing with when we talk about units of energy, is equal to a Newton meter. And when we talk about a Newton is a kilogram meter per second. So if we were to take newtons and convert it to kilogram meter per second squared and multiply it by meters, that gives us kilogram meter squared per second squared. So these are just some units to work with, so we're a little familiar with that. What we're going to deal with now is what's called heat capacity. And when we deal with heat capacity is defined as the quantity of heat. The symbol we're going to use for heat is Q.
Okay, it's a lowercase q. The quantity of heat either absorbed or released by an object when it experiences a temperature change. Now, this triangle here is a delta. Okay, this means a change in temperature of 1 degree Celsius, or we could say 1 Kelvin. Okay, the temperature change is equivalent whether the units are in Celsius or in Kelvin. So heat capacity, okay, which is a capital C, is the quantity of heat, Q, absorbed or released by a substance when it has a temperature change, delta T, of 1 degree Celsius or 1 Kelvin. Okay, now heat capacity depends on both the kind of matter that we're looking at and the amount of matter that's present. And when we go to calculate heat capacity, this is the equation we'd be dealing with. Again, this capital C is heat capacity. This lowercase q is the heat that's either absorbed or released by an object. And the delta T is the change in temperature that's caused by the absorbing or releasing of Q, or the amount of heat. So let's say that we have 2 pans. They're made of the same material. This one's a small pan. This one's a large pan. And we increase the temperature of both pans by 50 degrees Celsius. Well, let's look at the small pan first. If we wanted to calculate the heat capacity, or the quantity of heat absorbed per degree Celsius, we would take the energy that needs to be absorbed, which is 18,150 joules, and divide it by the temperature change. Okay, now we typically don't leave it like this, so we would just take 1800 or 18,150 joules divided by 50, and we get a heat capacity value of 363 joules per degree Celsius. So that means that 363 joules of energy have to be added in order to change the temperature of this small pan 1 degree Celsius. Now, let's look at the large pan. Okay, well, if we wanted to calculate the heat capacity, we would take the amount of heat that's required to warm up that larger pan. Okay, so 90,700 joules to raise the temperature the same amount, 50 degrees. So the heat capacity for the larger pan is 1,814 joules of energy has to be absorbed for every degree Celsius of temperature change for that larger pan. Now notice that we needed less energy to change the temperature of the smaller pan. We needed more energy to change the temperature of the larger pan, because heat capacity is dependent on what the material is. In this case, they're made of the same material, and how much we have. So now let's look at what's called the specific heat capacity. It's a little bit different. When we look at the specific heat capacity, okay, there's all different symbols that you might see for it. We're going to use a lowercase c. Okay, it is the quantity of heat, Q, required to raise the temperature of 1 gram of the substance by 1 degree Celsius or 1 Kelvin. So it's a little bit different because it depends on the amount of substance we have. So when we go to calculate the specific heat capacity, okay, we've got this lowercase c here, which is our abbreviation. It's Q okay, which is the heat required, how much energy is given off or absorbed, to raise the temperature of 1 gram of the material. So this is the M value, 1 degree Celsius. So this is our delta T. So the difference between the heat capacity and the specific heat capacity is this M. So let's look at the same scenario. We have our 2 pans, and we're going to warm up those 2 pans, and we're going to change the temperature 50 degrees total. And we want to calculate the specific heat capacity. Okay, well, we take the amount of energy that the small pan needed to warm up 50 degrees, and we divide it by the mass of the small pan. Okay, and we get a specific heat capacity of 0.449 joules per gram degree Celsius. So now let's look at the large pan, and then we're going to compare the numbers. When we look at the large pan, we're adding in a lot more energy because the pan is larger. We're dividing it now by the mass, which is much greater than what the mass of the smaller pan was, and the temperature change is the same. Well, look at what happens to the specific heat capacity. It's independent of how much material we have. If we have a small amount of the material, we need less energy. If we have a large amount of the material, we need more energy. But when we look at the specific heat capacity, it doesn't depend on the amount or the amount of the matter that we're heating up. It only depends on what it's made of. And every substance has a unique specific heat capacity. Substances that are good conductors of heat have low specific heat capacities, or specific heat, sometimes it's called for short, values. Like metals are good conductors of heat, so they tend to have small values for their specific heat. And substances that are insulators, not so good at conducting heat, would have much higher specific heat values. So we need to kind of understand the difference between heat capacity and specific heat capacity. So when we look at specific heat is measured in units of energy per temperature per mass. So joules per gram degree Celsius, or joules per gram Kelvin, or maybe joules per mole Kelvin. So a unit of energy per temperature per mass. And it's an intensive property. We talked about this at the beginning of the course. Those are properties that are independent of the amount of material. The molar heat capacity is very similar, but instead of talking about things in terms of grams, we're going to talk about things in terms of moles. So whereas we would see joules per gram degree Celsius or joules per gram Kelvin appear, molar heat capacity is joules per mole degree Celsius, or maybe kilojoules per mole Kelvin. And we can do conversions between the two. As long as we know what the substance is, we can look up the molar mass and do mass to mole or mole to mass conversions. We in no way need to memorize this, but just to kind of look, okay, this is an example of a specific heat table. So we have some substances that are listed here as their names. We have their symbols here, kind of gives us an indication of what their states are as well. And then it gives us what their specific heats are. And this particular table gives us the specific heat in terms of joules per gram degree Celsius. Again, there are different units that we could see for specific heats, and we just need to be careful to make sure that the values for the specific heats match up with the other information that's given to us in the question. And if we were to look way down here at the bottom of the table,
we're looking at substances that have very low specific heats. And if we look at what they are, okay, down here on the bottom, they're metals. Metals tend to be good conductors of heat. They tend to have lower specific heat capacities, and they require less energy to raise the temperature of 1 gram, 1 degree Celsius. If we were to look up here, now we're looking at specific heat values that are much higher. And actually, water is one that we're going to be dealing with in a lot of our problems in this unit. And water has a specific heat capacity value of 4.184 joules per gram degree Celsius. So for every gram of water that's raised 1 degree Celsius, 4.184 joules of energy needs to be added in. And that value is pretty high relative to many substances. And to give you kind of maybe an everyday example of this high specific heat value for water, think about if you live near a water source, okay, you live near the ocean, you live near a bay or a lake, it tends to be a little bit colder in the summertime and a little bit warmer in the wintertime relative to places that aren't near the water. And that's because the water that's near those areas needs a lot more energy to warm up or to cool down. So this is a conceptual problem. I don't want you to do any calculating, okay? We have a 10-gram sample of each of these substances. So 10 grams of iron, 10 grams of water, 10 grams of copper, 10 grams of aluminum. And to each of these substances, we're going to apply 250 joules of energy to them. Okay, well, that's going to cause the temperature to go up. Okay, when a substance absorbs energy from the surroundings, the temperature goes up. Out of these substances, again, I don't want you to do any math. I want you to just do some thinking. Which of these substances would you expect to have the greatest temperature change? Here's our equation, okay? The amount of energy that's being added is the same for all 4 substances. The mass is the same for all 4 substances. So we just want to see what's the relationship between specific heat and temperature change. The lower the specific heat value, the greater the temperature change. Okay, so if we were to look at these examples, copper has the lowest specific heat value, so it would have the greatest temperature change. And again, we could go through and calculate the temperature change for all of them, but we don't need to do that. It's just a relationship. Now let's do some problems. Okay, if you know the mass of an object and its specific heat, which you could actually look up on a table if it wasn't given to you in a question, you can determine the heat change, Q, due to a temperature change, delta T. Okay, so here's our equation. We just manipulated the equation from the last slide to solve for Q instead of C. So the amount of heat or the amount of energy required to raise the temperature of X grams, knowing the specific heat and knowing the temperature change. Now think about this equation for a second. If we have a larger sample size, we would need to add more energy in to raise the temperature. They're directly related. If we wanted to have a larger temperature change, we would need to add more energy in. They're directly related. And if we know the specific heat, because we know what the substance is, the larger the specific heat, the less of a conductor and the more of an insulator the substance would be,
and the larger the energy would be. Now, when we talk about temperature changes, delta T, we always calculate it by taking the final temperature. So TF stands for the final temperature minus the initial temperature. So TI stands for the initial temperature. Okay, so let's look at a question. Okay, we've got calculate the heat absorbed. That means we want to calculate Q. Calculate the heat absorbed when the temperature of 15.0 grams of water, so there's our mass, is raised from 25 or 20 degrees Celsius to 50 degrees Celsius. The temperature's going up. Okay, so Q is going to be positive because it's adding energy in. And it tells us that the specific heat is 4.184 joules per gram degree Celsius. So here's our equation. Okay, we are calculating Q. We know the mass. We know the specific heat, and we can calculate the temperature change. It's the final temperature minus the initial temperature, and see how much heat needed to be absorbed in order for that change to take place. Okay, so start with your equation, and I don't know whether it's just we're doing a shortcut, but some of us don't like to write down equations. I would strongly suggest that you write down the equation first. And actually the order of the variables here is a little bit different than here. It doesn't really matter because multiplying is independent of the order. So it's just a little bit different order. Plug in your numbers. Make sure your numbers have units with them. Okay, some math problems we do, I see some numbers that don't have any units on them. Okay, they're equally as important. And I can tell you, for people who don't do shortcuts on these kinds of problems, tend to do much better than people who just do partial work. So, really try to do all that. Take a look at the units when you plug them in, okay? Because some of the units are going to cancel out, and you'll see the units that you're going to end up with. And be careful with significant digits when you go to get your answer. And the 4.184 doesn't count towards significant digits because it's a constant. 4.184 joules per gram degree Celsius. We've got 15.0 grams for our mass. The final temperature is 50.0. The initial temperature was 20.0. So when we get our temperature change, that's going to give us 30.0. That has 3 significant digits in it. The 15.0 has 3 significant digits in it. So when we go to get our answer, we're going to want 3 significant digits. Now, if you left that at 1880, that's okay. Although the number is bigger than in the hundreds place, probably better to write it in scientific notation, but you didn't necessarily have to do that. And then let's look at the units. We've got grams here in the denominator, and we've got grams here in the numerator. So grams cancels out. We've got degrees Celsius here in the numerator and degrees Celsius here in the denominator. So degrees Celsius cancels out. That's where the units of joules come from. And those are the units for heat. So 1.88 times 10 to the third joules of energy needs to be absorbed by 15.0 grams of water in order to give us a 30-degree temperature change. And again, that was pointed out before, the temperature change is a positive value because energy has to be added in order for that temperature to go up. So this is the amount of energy that was absorbed by the water. If the question was kind of worded backwards and it said calculate the amount of heat that was released when it went from 50 to 20, the value would be the same. It would just be negative because that's the amount of energy that's being released or given off. So here's another question, same concept, but we're going to calculate a different variable. So there is going to be a little bit of algebra involved in the problem. So it says, what will be the final temperature
of a 50.00 gram silver ring at 37.00 degrees Celsius that gives off 25.0 joules of heat to the surroundings. And it gives us the specific heat for silver. We could look it up on a table, but it's given to us in the question, 0.235 joules per gram degree Celsius. Now, energy is being given off. That means the final temperature is going to be less than the initial temperature. Just something to think about. So because of that, the value is going to be a negative value. Here's our equation. The first thing we want to do is solve for delta T. So you do a little bit of algebra. You want to get rid of C and you want to get rid of M off the right-hand side of the equation. Okay, so here's our new equation. Delta T equals Q divided by C divided by M. So you know Q, you were given that value, although it's going to be a negative value, okay, because energy is being given off. So we know the specific heat, 0.32 or 235. We know the mass, 50.00. Calculate first just the temperature change. Oh, I went too fast. I was going to say just the temperature change, not the final temperature, but we got the final temperature in there, so that's okay. So we're going to plug in negative 25 degrees Celsius. This should say temperature decreases. It shouldn't say temperature increases. So negative 25 joules. Okay, our mass is 50.00 grams. The specific heat is 0.235 joules per gram degree Celsius. Okay, notice that grams cancels out and joules cancels out. And we're left with 1 over degrees Celsius. That's where the degree Celsius comes from. So the temperature change is 2.13 degrees Celsius. This should actually say 25.0, so we've got an extra significant digit. So we want to calculate T final. Okay, we know the temperature change and we know the initial temperature. So again, just a little bit of algebra. We want to get T final by itself. We would have to add T initial to both sides. So we've got negative 2.13 plus 200 or plus 37 degrees Celsius gives us 34.87 degrees Celsius. Now, remember that when you add or subtract, you're looking at the number of decimal places to decide where you want to round off. Since both of these numbers have digits in the hundredth place, you want your answer to be in the 100th place. Again, this should say 25.0, so that then we have 3 significant digits here, 4 significant digits here. That's where this 3 significant digits comes from. And then we've got 2 decimal places, 2 decimal places. We want 2 decimal places in our answer. Again, this is a typo. It should say the temperature decreases because we're giving off energy. That's a typo there. Okay, really, we're looking at this equation. There are 4 variables. This is the amount Q, is the amount of energy that's given off or released. C is the specific heat, which is specific to a substance. M is the mass, or the amount of that substance we have. And delta T is how much we want to change the temperature. Okay, out of those 4 variables, you'd be given 3, and you have to figure out what the 4th one is. Let's look at this one. Now, we want to calculate the specific heat. Okay, so it says calculate the specific heat of a metal. If 2.05 kilojoules of heat, okay, that unit's going to have to be changed to joules, is needed to raise the temperature of 200 grams from 19 to 98. Don't worry about identifying the metal yet. Okay, so you've got your equation. This time, in order to identify the metal, we need to calculate the specific heat. We know Q.
we know M and we know delta T. So we're going to be calculating the specific heat. So let's do that part first. And then we'll go on to the identifying the metal part. Okay, so to calculate C, you're going to have to divide both sides by M. And you're going to have to divide both sides by delta T. Remember again, the way that you calculate delta T is taking the final value minus the initial value. Remember that we want the specific heat in joules per gram degree Celsius. So we don't have numbers that are super small. So if we've got why is that number not the same number? Is that just a typo there? That's the number we get for an answer, right? There should be a 0 there. I don't know where that 3 came from. 2.05 becomes 2050. Again, there should be a 0 here. That's a typo. Joules. We'll divide it by 200 and we'll divide it by our temperature change. Okay, we're going to have 3 significant digits in our mass and 3 significant digits in our temperature change. We have 3 significant digits in our specific heat. And our units, nothing cancels out, joules per gram degree Celsius, which means for this metal, 0.130 joules of energy needs to be absorbed for every gram that's raised a degree Celsius. Now, once we know the specific heat, we can identify the metal. And the way we would do that is by looking at a table. So I called back up that table that we had a couple of slides ago and see if you can identify what the metal is. Okay, so we look through there, we find 0.130, and the metal is in fact lead. And you can use these kinds of data to identify what a metal is. So now let's look at what's called calorimetry. And when we deal with calorimetry, okay, it is just a lab technique that's used to measure the amount of heat that's given off or absorbed by a substance. Okay, so we were looking at these numbers and doing some math problems with them. So now we're going to deal a little bit with where those numbers come from or how we can measure them in a lab and do some calculations with that. So when we talk about the heat that's exchanged, okay, we're dealing with what are called calorimeters. Calorimeters are just calibrated objects. Okay, the temperature change measured by the calorimeter is used to calculate or derive the amount of heat transferred in the process. Okay, the energy stays in the calorimeter. Okay, it's something that's insulated so that we're only dealing with energy that's being transferred within that calorimeter. We really don't have to worry about energy being transferred between the contents of the calorimeter and the environment or the surroundings. So if we were to look, we've got 2 examples here. So this is our calorimeter, and this is what we're studying. Okay, so we have some kind of a process here that's taking place. Again, we'll look at specifics in a couple minutes. This is just kind of generalities. So we've got a system here, and then the surroundings are maybe a solution. And whatever process is taking place here is giving off energy to the surroundings, to the solution. Well, when that takes place, we're talking about an exothermic process. And it would cause the surroundings to have an increase in temperature. If we were to look at the reverse, okay, we've got this calorimeter here, which insulates, the inside from the environment. And we've got our system here, whatever it might be. And when that process takes place, energy is absorbed from the surroundings into the system. Well, now we're looking at an endothermic process. It's always relative to the system. So the system's absorbing energy here as opposed to giving off energy here. And when energy is absorbed by the system, in turn, it's being lost by the surroundings, and the temperature of the surroundings goes down. So let me just cover something here. We might want to just like jot down a little extra note here. An exothermic process has an increase in the surroundings. An endothermic process has a decrease in its surroundings, because we typically measure the surroundings and not the system, just by nature of what we're doing. So let's say that we have a hot piece of metal and we put it into some cold water. Classic calorimetry question. Well, energy is conserved. Okay, we dealt with that at the beginning of the unit. That means that energy can't be created or destroyed. So the total amount of energy inside that calorimeter is a constant. So the heat that's absorbed by the water in this scenario will be equal to the heat that's released by the metal in this scenario. So we have this little scenario here. This is our metal, okay, which is our system. And the water are the surroundings. And energy is going to be transferred from the system into the surroundings. We're measuring the temperature of the surroundings. So we're going to notice that the temperature of the surroundings, or the temperature of the water, goes up. Now, that means that the metal is losing energy. So we're going to put a negative sign here. Okay, that just represents the metal losing energy or losing heat. And we've got the water gaining energy. We could put a positive sign here. We don't necessarily have to. It's kind of assumed. And because of the law of conservation of energy, the energy lost by the metal equals the energy gained by the water. Well, we have an equation that enables us to calculate Q. So we'll just take that equation and do a little substitution. The energy that's lost by the metal can be calculated by taking the mass of the metal times the specific heat of the metal times the temperature change for the metal. Again, we're going to put this negative sign here to represent the fact that the metal's losing energy. We can calculate the amount of energy that the water gains by taking the mass of the water times the specific heat of the water times the temperature change for the water. And again, this side of the equation is positive because the water is gaining energy. And theoretically, the energy that's lost by the metal equals the amount of energy that's gained by the water. So now we've kind of complicated the equation just a little bit, and we've got 6 variables. We'd be given most of those variables, and we'd have a variable that's missing, and we can calculate the missing variable. So here's a question. Okay, taking the same concept we just talked about. So we have 19.6 grams of a metal is heated to 61.67 degrees Celsius and placed in 26.70 grams of water in a coffee cup calorimeter. Okay, that's kind of a cheap lab calorimeter that keeps the energy inside the container and allows very little energy transfer into the room. The temperature of the water goes up. That makes sense because the water is gaining energy from 25 degrees Celsius to 30 degrees Celsius. What's the specific heat of the metal? All right, now this question is different from the questions we were doing before because now it talks about 2 different substances. So we're looking at an energy transfer problem. So we need to decide what's losing energy and what's gaining energy, and then figure out what variables we have. So the metal is going to be losing energy because it's at a higher temperature. The water is going to be gaining energy because it's at a lower temperature. The metal is going to release energy. The water is going to absorb energy or heat. The amount of heat absorbed and released is the same. So Q lost by the metal
equals Q gained by the water. And the final temperature of the metal and the water will be the same. The metal is going to lose energy. Okay, the temperature is going to go from 61.67 degrees Celsius to something less than that. The water is going to gain energy and its temperature is going to go up. And it tells us that the final temperature of the water is 30.00 degrees Celsius. Well, that means this is also the temperature of the metal at the end, because the energy is going to continue to be transferred from the metal to the water until the two temperatures are the same. So here's our equation. So this side of the equation is all the stuff about the metal. The metal is losing energy, so that's why we have that negative sign. We've got the mass of the metal times the specific heat of the metal times the temperature change for the metal. And again, temperature change is the final minus the initial temperature. And this side of the equation is the water side of the equation. So we have the mass of the water times the specific heat of the water times the temperature change for the water, again, being final minus initial. Now, we want to find the specific heat for the metal. So we're going to do a little bit of algebra. Okay, we're going to need to get rid of the mass of the metal. So we would divide both sides by negative m. And we want to get rid of the temperature change. So we're going to divide both sides by the final minus the initial for the metal. And we isolate the specific heat of the metal. Now, all of the numbers on the right-hand side are given to us in the question. So what you need to do is plug in the mass of the water. The specific heat of the water isn't listed there. I'll tell you what that is again. You're going to use it often enough that you're going to remember it, but it's 4.184 joules per gram degrees Celsius. And then you're going to take the final temperature of the water and subtract the initial temperature. Okay, all that together is going to give you your numerator. You're going to take the negative mass of the metal times the temperature change for the metal, which will be final minus initial, keeping in mind that the final temperature of the metal is the same as the final temperature of the water, even though it doesn't state that. And see what you get for the specific heat of the metal. Okay, so the mass of the water is 26.70 grams. The specific heat for water, this is a constant, 4.184 joules per gram degrees Celsius. The final temperature was 30 degrees. The initial temperature was 25 degrees. Okay, the mass of the metal was 19.6 grams. Even though it doesn't state it, the final temperature of the metal was 30. The initial temperature was 61.67. Now, the temperature change is negative, but you're multiplying it by a negative sign. Your specific heat values can never be negative values because you're talking about how much energy is required to raise the temperature of 1 gram of a substance 1 degree Celsius. You have to add energy in to make the temperature go up. So when we plug that in, I agree, we get 0.900. Now units, the grams here cancels out with the grams here. The degrees Celsius here cancels out with the degrees Celsius here. And that's where we get that joules per gram degrees Celsius. And then if the question said, you know, what's the metal, we could do like we did in the previous problem where you're look at a table and just match it up.